because it needed some other stuff. So section 8.1, the binomial theorem. So let's recall A plus the special product formulas. A plus B to the 0 is just 1. I'll write that as 1. A to the 0, B to the 0. A plus B is just, well, A plus B. I'll write that as 1, A to the 1, B 0, plus 1, A to the 0, B to the 1. A plus B squared is A squared plus 2AB plus B squared. A plus B cubed, A cubed plus 3A squared B plus 3AB squared plus B cubed. A to the 4th, A to the 4th plus 4A cubed B plus 6A squared B squared plus 4AB cubed plus B to the 4th. So now, notice the following. I can put, well, ones here just to make it look nice. And for the ones that I start here, I'll put in B zeros and A zeros on this side. And if I have an A or a B, I'll put A the first and B the first. Okay. So now I look at the following. If I look at the exponent for each of these, then the sum of the exponents are always going to equal that exponent. So 4 is 4 plus 0, 3 plus 1, 2 plus 2, 1 plus 3, 0 plus 4. So the exponent is the same as the sum of the exponents for A and B. Next, the exponents go in a nice pattern. 4, 3, 2, 1, 0 for A, 2, 3, 4 for B, and that occurs for all of them. Next, the coefficients are just the coefficients of Pascal's triangle. 1, 1, 1, drop down to 1. 1 plus 1 is 2, drop down to 1. 1, 1 plus 2 is 3. 2 plus 1 is 3, drop down to 1. Drop down to 1. 1 plus 3, 4. 3 plus 3, 6. 3 plus 1, 4. Drop down to 1. So all of these coefficients are just the numbers that we obtained from Pascal's triangle. And so the coefficients in these formulas are denoted by well, the binomial coefficient, B sub k, and the coefficient for Pascal's triangle, the number in Pascal's triangle was denoted by NCK. So these are really the same. These, if you recall, factorial was defined as follows. 0 factorial was 1. N factorial is just n times n minus 1 factorial for any natural number n. The binomial coefficient was defined as follows. For any natural number w, for any natural n, for any whole number n, for any whole number k, where k is less than or equal to n, we define the NCK as n factorial over k factorial to n minus k factorial. And we will also call that the binomial coefficient. And it's denoted by this weird floating number, n over k. N is floating over k, and write it in the parentheses. We will also define the binomial coefficient as, well, sort of our simplifying formula. It's just n times n minus 1 times n minus 2 times dot, 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 n minus k plus 1. So I'm just multiplying this n, these terms here, k terms multiplied together over k factorial. And so I define the binomial coefficient for any whole number k and for any complex number n as n minus 1, n minus 2, dot, 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 n minus k plus 1. So that's just multiplying k terms over k factorial. So we had the properties of, which we've shown, of the binomial coefficient, that NC0 was 1, NC1 was 1, NCK minus 1 plus NCK was N plus 1 CK. Then I can use this to prove the binomial theorem, which says that this idea here to expand to have all these special product formulas works. A plus b to the n is just the sum, k equaling 0 to n, of the binomial coefficient, nck, times a to the n minus k, times b to the k. So let's prove this by induction. So let's first do the initial case. So if I let n equals 0, then a plus b to the 0 is 1. If I let n equals 0 here, then the sum k equaling 0 to 0 of nck, well, in this case 0 ck, a to the n minus 1, 0 minus 1, 0 minus k, b to the k, is, well, this is just 0 c0, which is 1, a to the, well, in this case k is 0, so a to the 0, b to the 0, 1 times 1 times 1 is 1. And so I've shown that these are equal. And so the initial case works. For the induction case, assume that the sum j equaling 0 to k of kcj, a to the k minus j, b to the j, is equal to a plus b to the k. So now let's look at a plus b to the k plus 1. That's just a plus b times a plus b to the k. But a plus b to the k by the induction hypothesis is just the sum j equaling 0 to k of kcj, a to the power k minus j bj. Let's distribute. So let's multiply this first term by a. If I multiply this first term by a, this just becomes a to the power k plus 1 minus j. Plus, let's multiply this by b. So this becomes, everything's the same except this becomes b to the j plus 1. Let's write out the first term. And so when j is equal to 0, this is just k c0, a to the power k plus 1 minus 0, b to the 0, plus everything going from 1 to k. Now let's write out the last term of this. So j equaling 0 to k minus 1 of these, plus the last term. So let's plug in k for j. So k ck, a to the k minus k, times b to the k plus 1. kc0 is 1. b to the 0 is 1. K plus 1 minus 0 is just k plus 1. So this first term is a to the k plus 1. Let's look at the last term. kck is just 1. K minus k is 0. A to the 0 is 1. So this last term here is just b to the k plus 1. Let's just rewrite this term. So this is the sum, j equaling 1 to k, kcj, a to the k plus 1 minus j. Let's put a k plus 1 in parentheses, b to the j. Plus, now for this term, I'm going to let I equal j plus 1. And so when j is 0, I is 1. When j is k minus 1, I is k. K is still k. J, I said, was, well, I was k, j plus 1. Therefore, j is I minus 1. I replace j by I minus 1. And j plus 1 is just I. Now, just to make things look nicer, instead of writing i's here, I'll write these as j's. And so now, I'll combine these terms. Since notice, this is a to the, this is a sum, j equaling 1 to k. This is a to the k plus 1 minus j. These are the same. And this is a b to the j. So I will now rewrite this as, well, this is a k to the j, kcj, and this is a plus kcj minus 1. But I know that that's equal to, by the property that we've shown in, what if it was section 8.5 or something, this is just k plus 1 cj. Next, I know that k plus 1 c0 is 1, so I'll just write that as a 1 here. I know subtracting 0 from anything won't change anything, and then I know that b to the 0 is 1. Next, for this last term, k plus 1 c k plus 1 is just 1, so I can write that in front, not do anything. K plus 1 minus k plus 1 is 0. A to the 0 is 1, so I can write this out in front. But now, this is just the first term when j, this is the same as this when j is 0. And this is the same as this when j is k plus 1. So now I can replace these with the sum j equaling 0 to k plus 1 of k plus 1 cj, a to the k plus 1 minus j times bj, b to the power j. So therefore, by the principle, so now notice that this formula now works when I replace k by k plus 1. So therefore, by the principle of mathematical induction, a plus b to the n is equal to the sum j equaling 0 to n ncj times a to the power n minus j times b to the power j. And this works for every natural number, for every whole number n. Okay, and so notice that if I define n, the binomial coefficient, as n times n minus 1 dot 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 for those k terms over k factorial, that n a plus b to the n is equal to the sum j equaling 0 to infinity of ncj, a to the n minus j, b to the j, and this will be true for every actually complex number, for every n, and n in this case could even be a complex number. You'll show this later in, in further courses, but not in this course. So this formula actually still works for very, very general powers. Oops. Let's do this for, okay. So let me, see if I can move this. Okay, so let me do some problems. On page 729, evaluate each expression. 5 factorial minus 2 factorial. 5 factorial, 5, 4, 3, 2, 1. 2 factorial, 2, 1. 120 minus 2 is 118. Let me do problem number 21. Use Pascal's triangle to expand each binomial. Okay, so let's do that. So let me use this binomial theorem. Okay, so let me use the binomial theorem. I don't know. What did I use? Yeah, let's use K. K of NCK. A N minus K B to the K. Okay, so let's do this. So this is equal to in this case, I'm going to use the fact that is found in Pascal's triangle. Okay, so let me do this. So I want to go all the way up to 6 or 5. 5. I want to go up to 5. So let's do Pascal's triangle. 1, 2, 1, 1, 3, 3, 1, 1, 4, 4, 1, 4, 3 plus 3, 6. 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Okay, so now this will tell me the coefficients that I need. And so this is A plus B to the 5th. And you can do this so long as, well, the exponent is small. So this is going to be 1, A to the 5th, B to the 0, plus 5, B to the 4, A to the 4. Actually, maybe I'll write it here so I have more room. So it's 5, A4, B1, 10, A3, B2, 10, A2, B3, 5, A1, B4, 1, A0, B5. Okay, so let's simplify this a little bit more. So this is A to the 5th plus 5, A to the 4th, B, 10A cubed, B squared, 10A squared, B cubed, 5ab4, b5. And that is your special product formula for higher power than we gave you from before, just using Pascal's triangle. Let me do problem 29. So again, we're going to be using Pascal's triangle. So I'll maybe write it here. 1, 1, 2, 1, 1, 3, 3, 1. Okay, so using Pascal's triangle, I get that this is equal to 1, 2x cubed, y to the 0, plus 3, 2x squared, y to the 1, plus 3, 2x to the 1, y to the 2, plus 1, 2x to the 0, y to the 3. Okay? And so this is equal to 2 cubed is 8. And maybe I will just write the answer. And so 2 cubed is 8. Y the 0 is just 1. 2 squared is 4. Times 3 is 12. X squared y. 2 times 3 is 6. And, well, 2 to the 0 is 1. And so this is your formula. So this is how you expand that particular binomial. Use the binomial theorem to expand each binomial. The binomial theorem. Okay, so let me write the binomial theorem. A plus B to the n, sum k equaling 0 to n. Oh, I hope I wrote 0 when I wrote it before. Yes, I did. Okay, I was just being paranoid for a second. K equaling 0 to n of n ck a n minus k b to the k. Okay, so let's do x plus y divided by 2 to the 4th is equal to 4c0 a to the power 4 minus 0. Notice 4 minus 0. B to the 0. Notice 0. Plus 4c1 x to the 4 minus 1 y over 2 to the 1 plus 4c2 x to the 4 minus 2 y over 2 to the 2 plus 4c3 x to the 4 minus 3 y over 2 to the 3 plus lastly 4c4 x to the 4 minus 4 y over 2 to the 4. Now I'll need another page. So this is equal to 4c0 is just 1. And this is x to the fourth. And maybe I'll use a little bit more space. 4c1 is 4. X cubed. Y over 2 to the first is, well, y divided by 2. 4c2 is 6. X squared, 4 minus 2 is 2. And y over 2 squared is, well, y squared over 4. Plus 4c3 is 4. X to the first, y cubed over 8. Plus 1 times 1, y to the fourth over 16. So this is equal to x to the fourth plus 4 divided by 2 is 2, x cubed y, plus 6 fourths, 3 halves, x squared y squared, plus 4 divided by 8, 1 half, xy cubed, plus 1 over 16, y to the fourth. And that is your answer using the binomial theorem. Find the required term in your binomial expansion. Okay, so notice that every term in my binomial expansion to this form, nk a to the n minus k b to the k. So what is the third term? Let me just go up here. So notice, first term, k is 0. Second term, k is 1. Third term, k is 2. So really, I'm going to be replacing this k here by 2. This n is, well, our power, 8. So I'm replacing that by 8. The a's and b's are, well, what our a's and b's are. So let's figure out the third term in this. And so the third term in this is going to equal a c2 times, well, in this case, it's an a. 8 minus 2 is 6. So notice I just subtract this. And then minus rad 3 to the power 2. So I have to figure out what AC2 is. So it's 8 times 7. So 4 times 7 is 28. So this is 28. A to the 6 times a negative rad 3 squared is 3. And so this is 60, 84, a to the 6. Let me actually do this on a calculator just to check. 8C2, 8. Takes a while to do this on a calculator. 8C2 is 28, 84. Okay, good. And so this is 84, a to the 6 is the third term in our expansion. Third term meaning starting with a to the eighth as being the first term, other direction. So this would, but okay. So, but we're not in statistics. So let's find the fifth term. So again, recall that since we started at 0, the fifth term is going to be, and this is n. So n C4 of a to the n minus 4 times negative b to the power 4. So this will equal NC4, and that of course is going to depend on what n is, so it's just NC4 over times a to the n minus 4. However, a negative 1 to the 4th is just 1. So I can write this as b to the 4. And that is your fifth term in your binomial expansion. 63. So let me do problem 63. Find the constant term in the expansion time a minus 1 over a to the power 10. Okay, so let's do that. So recall that in the binomial expansion, every term looks something like this: a to the n minus k, b to the k. And I want it to be a constant term. So it means that I don't want any powers. And so somehow I don't care about, at least initially, I just want at the end. So let's say that this is let's actually do this expansion. So each term in your expansion is going to look something like this. And at the end, I want it to not have any powers of a. So I don't really care about any of the constants at this moment. So let me just only worry about things involving variables. So it'll be a to the power 10 minus k. I don't care about the negative. So 1 over a to the power k. I want that to eventually equal a to the 0. Figure out what k is. That will tell me the term. Once I know the term, then I can figure out the constant. So I first want to figure out what term is constant. So I guess the first question is determine constant. Determine k. Well, which term is constant? Which term is constant? So really, that's the first thing I want to do. And so this is a to the 10 minus k. A to the minus k equal a to the 0. So this is a to the 10 minus 2k equals a to the 0. Since the exponential function is injective, since the base is the same, I'm assuming a is not 0. Since the base is the same, and since these values are equal, then I must have that are equal. And so I have that 2k is equal to 10, so k is equal to 5. And so it's a term when k is 5. And so I have, let's look at the sixth term in this expansion. And so it's a, so it's 5, it's I'm sorry, I forget what, was it 10? It was 10 C5 a to the 5 negative 1 over a to the 5 also. So this is equal to 10C5, and so 10C5 is 252 a to the 5th and a negative 1 over a to the 5th is a negative a to the 5th. And so this is equal to 252. So the a to the 5ths cancel, which is what you hoped would happen. And so the constant term, so once I do an expansion, I'll find that in this binomial expansion, I just get a number. And the number that I get is 252. And that's it. Okay, so that finishes off section 8.1, which finishes off the course. And so that's it.